Hey everyone, welcome to the next lesson on hydrocarbons. In the first three lessons, we went over alkanes, their saturation, their formula, their naming, how to draw them, bond line structure, and more. So that's a lot of the heavy lifting, and what we're going to do today is apply what we learned about alkanes to the next two types of hydrocarbons that we learn about in organic chemistry, which are called alkenes and alkynes. Great, so alkanes, a little bit of review. They only contain single bonds or sigma bonds. As a result, you can see the molecule butane. It has 4 carbons, so we use the prefix but, and since it only has single bonds, we end it with ane, butane. Great. So that's the suffix we use for alkanes. They only contain single bonds. The formula is CnH2n plus 2. We learned this. The 2n plus 2 for the amount of hydrogens comes from the fact that every single carbon is bonded to at least 2 hydrogens, whereas the outer carbons, the ones on the edges, contain 2 extra bonds to 2 hydrogens because they're only bonded to 1 carbon. As a result, we say that this is a saturated hydrocarbon because alkanes have all the possible bonds they could have to all possible hydrogens. Great. Moving on to alkenes. This one's new. But alkenes are simply hydrocarbons that contain at least 1 double bond or 1 pi bond. As we can see the molecule, there's 4 carbons, but there's the presence of 1 pi bond, so the prefix will be but, but since due to the presence of that pi bond or double bond, we will end with ene instead, so butene. Great. The formula is CnH2n. Why is this? Well, as we discussed in the alkane lessons, the presence of a pi bond actually reduces the hydrogens the carbons are bonded to by 2. As a result, we can remove 2 from the standard alkane formula and we're left with CnH2n. Due to the presence of the pi bond removing the capability of bonding to 2 hydrogens, we call this molecule or hydrocarbon unsaturated. So alkenes and alkynes are unsaturated molecules. Why is this? Well, they have 1 pi bond, and we know a pi bond removes 2 hydrogens, which we call to be 1 degree of unsaturation. Yeah? Great. Moving on to alkynes. Alkynes contain at least 1 triple bond or 2 pi bonds. But what I mean by 2 pi bonds is like 2 pi bonds in the same bond, but just 1 triple bond. Let's not complicate it. For example, the molecule shown for the alkyne contains 4 carbons, so the prefix will be but, and due to the presence of a triple bond, it'll end with ine, which is the suffix for alkynes. So the full molecule's name will be butine. So alkynes contain at least 1 triple bond, and their formula is CnH2n minus 2. We subtract 2 due to the presence of 2 pi bonds. We know each pi bond removes 2 hydrogens. So if we have 2 pi bonds, that will remove 4 hydrogens in total. And we can subtract 4 from the standard alkane formula, and we end up with the alkyne formula. We call alkynes to be unsaturated molecules because they do not have all the possible bonds with hydrogen that they can have. And due to the loss of 4 hydrogens, aka the presence of 2 pi bonds, we call a triple bond or an alkyne to count as 2 degrees of unsaturation. This is useful so that when you have to draw isomers, you know when you get 1 degree versus 2 degrees of unsaturation, okay, I know what 1 degree can be, aka a pi bond, and I know that 2 degrees of unsaturation can be a triple bond. Great. A way I like to memorize alkanes, alkenes, and alkynes is the first letter in the suffix. A comes before E comes before Y. Single bond comes before double bond comes before triple bond. So that's the way I use a mnemonic or some sort of alphabetical logic to think of the order of the way the bonds came as well. Great. Moving on to some hydrocarbon properties, I cannot express the importance of knowing your bond lengths. A single bond is the longest bond, whereas a triple bond is the shortest bond in length. So as you add pi bonds, the length of the bond will decrease. Next, Something very, very important is that single bonds have free rotation. This means that the single bond can rotate, and as a result, two separate groups or two groups of atoms in the same molecule can be rotating relative to one another. Why do single bonds rotate? Well, it's due to the electron cloud repulsion of adjacent atoms, right? Atoms that are next to each other. Each atom has an electron cloud, and these electron clouds repel. Due to the repulsion, there will be energy of motion because they don't want to be in an unstable state. So they will rotate to get to a stabler state. So there are states of where it's energetically more favorable to be in that position. Those are called conformers, which you don't have to know for now, but it's useful to know that single bonds have free rotation and they prefer certain states over others. So they always rotate, right? They're always rotating. Now, why is this important? Well, this is important because double and triple bonds, aka the presence of pi bonds, does not allow free rotation. The way pi bonds are created through double and triple bonds is that pi bonds involve certain orbital overlaps that prevents that free rotation, right? So it locks the molecule into a certain state even if it's energetically unfavorable. So due to the creation of different versions of these molecules, we will now dive into what are called geometrical isomers, which is when it's the same molecule. It's not a different arrangement as we saw with structural isomers where the branching changed and such. It will be the same molecule just in a slightly different position, which we will get into when we go over alkene nomenclature. Great. Last thing. This might come up on the exam, it might not, but it's useful knowledge. Oops, sorry about that. Oh, anywho. Wow, that's a lot of images, but as the amount of carbon stays constant, as you can see, each of those three molecules has the same amount of carbons, which is 5. As the branching increases, or aka as the number of the main parent chain decreases and the rest of the carbons are added as substituent groups, you can see that the surface area decreases, right? Due to that decreased surface area, each molecule will have a less polarizable electron cloud, which will result in weaker dispersion forces. And if we have weaker dispersion forces, then that means it will take less energy to break them, and as a result, each molecule will have a lower boiling point than the other as branching increases. That's pretty much the important properties for hydrocarbons and the types of hydrocarbons. Thank you so much. I'll see you in the next lesson where we will go over alkene nomenclature. Thank you.